Hi, I'm Ryan Nicol, CTO at DSA Ocean, and today I want to talk about setting up a mooring for a large buoy directly in ProteusDS Simulation Toolbox. So why you would want to do this is that sometimes, particularly in cases where you're concerned about the rotation and inertia of the buoy, and you want to get into more detail with that, you have to model it with a rigid body. You could set up moorings like this with Oceanographic Designer. And certainly that's fine if you're mainly interested in exploring the driving dynamics in the mooring and the loads, the maximal loads and waves and currents and things like that, and mooring deflection. But in some cases, particularly with shallow water moorings, it's quite fast to set everything up in Simulation Toolbox directly along with a rigid body buoy model. So as I said, you could do something in Oceanographic Designer, and you can see here we have, you can change the surface buoy here, for example. I'm going to look specifically at the surface buoy DB8000 by Mobilis, just kind of arbitrarily, but just because. And let's say we're working in a really shallow water depth of, say, 30 meters. So you could work with setting up the mooring here, replace this with chain, and so on and so forth. But again, if you're worried about the rotation dynamics of the buoy, and you want to get more into the detailed buoy modeling, for shallow water moorings, it can be really quick to do that in Simulation Toolbox. So let's jump over to Simulation Toolbox and see what that looks like. So I'm just clicking on the visualizer here, and we will hit on settings. I like to show the water surface here just for a point of reference. So we don't have anything in here. Let's go to environment, set this to 30 meters water depth. Okay, so the first thing we're going to need is a rigid body. We'll call it DB8000. And we need to do a few things with this. As you can see, we only have our center of gravity. There's no hull there or anything like that. So you could dig around and look for a spec sheet or information on this buoy on the internet, but we do have many spec sheets linked to in our parts editor. So if you look for the parts editor app, ProteusDS parts editor, you'll see DB8000, and we can even click on the link here, but we have pretty much everything we need here to do a pretty good sized and detailed model. So there's the DB8000 data buoy. It's quite a big buoy. It's got a diameter of 3 meters. You can see from the particulars here. And I'm going to keep this to the side here as we work with this. So first thing first, we can see the mass here. So we'll put that in, 3260. You'd have to estimate the inertia from the supplier or the CAD package that you have, that you're working this out in. For now, we're just going to use those as placeholders. Now we make rigid body hull components for the model. So there's more than one way to do this. A really quick and easy way to do this is using the built-in cylinder parametric shapes. So I'm going to call this one 3 meter hull for a cylinder shape. If we right click on that and go to feature definition, you can see that we've got this cylinder here, and it's we want to change the numbers here to be 3 meter diameter. And you can see here we've got 1.71. It's a little blocky, so I might want to add a few angular segments here to just kind of make it look a little bit more like cylinder. You don't have to go overkill with it. Just something to get started is the main thing. Okay, we orient everything relative to the rigid body reference frame. So what I like to do to keep track of where everything is relative to that rigid body reference frame is I like to set everything up with the rigid body reference frame set up at the bottom of the flotation hull. So with that frame, the cylinder frame's in the middle of the cylinder hull. So we will do this at -0.855. There, and you can see the center of gravity indicator here. Now if I click on this toggle mesh faces on and off, we can see through the cylinder there's our feature frame location here. Currently that's the center of gravity indicator. So we can move the center of gravity just up a bit, maybe about there. Again, you would get feedback from the assessment of your specific buoy configuration, but it's a starting point. If you look back at the spec sheet, you can see there's a little sort of mast here and a little keel, so we'll add 2 components for those quickly. Cylinder, call this mast, and I'll right click on this, go to feature definition. So these aren't found in our local project library. We'll just create that in the local library here. Sort of looks like it's about 1.5 meter diameter. If we go back to the website here, it's 2.3 meters tall, say. You could even go a little bit higher than that, but we're just getting started here. And the mast is primarily like an open frame. So what I want to do is turn off buoyancy from that, because I don't want to get this is hydrostatic frog Krylov, which does dynamic and static pressure over that cylinder. We want to turn that off, otherwise we'll get bonus buoyancy from that. I don't want that. Keeping the system afloat. So this is about 3 meters tall, plus 1.71 is 1.71 plus half of that, 1.5, 3.21. Oops. Keep all those numbers on a line there. It's a little, you can see it's there's a little bit of a gap. That won't hurt anything. Maybe I'll move it down a little bit. A little bit lower, 2.7. I feel like I did the math not quite right on that. That's all right. Okay, it doesn't matter if there's overlap. That doesn't cause any conflict or collision or anything like that. It's just all part of the buoy. And we'll do a keel now. And this keel is going to be this part here. So we're 9.9 meter diameter, roughly. That's pretty close. And I don't have a direct dimension for this, but it looks like it's going to be about sort of 1.5 meters or so. And you can refine these numbers as needed. Now, we'll put this down in Z 0.75, a little bit there. Okay. And that's our buoy. So let's save this project right now. I'm going to select this folder and then we'll call this setup, where I'm just getting things started here. Okay, so now we need something to represent the mooring. What I'm going to do is I like having the anchor at the 0, 0 location, but then on the seabed, and then the mooring moves away from that point. So I'm not going to try to solve for the static deflection of the mooring, but we'll put this buoy, say 50 meters along the X direction, and we'll have the environmental conditions going in that direction as well. It's just as a starting point, we're going to let the simulation with wind and currents and waves push it to where it needs to go to and assess the dynamic loads that way. So we'll create the mooring now with a cable. And first thing we'll do here is just make sure we set node end to static. That's going to be where the anchor is. And before we specify into the geometry, we want to get some parts information from the library. Just close Oceanographic Designer here. So here's our parts editor. What I'm going to do is just pick a pretty hefty chain. Grade 3 studless, let's say 30 millimeters of chain. And we go view selected part in input format. So we copy, and then we can, what I've done is I've made a new decable segment. We'll rename this feature. Oh, sorry, let's make a new one. Add feature, decable segment, and we'll call this chain 30 millimeter. We have default properties for all the mechanical properties for the elements, and we'll hit Control A, delete it all, and then hit Control V, and it's pasted in this information for that grade 3 studless chain. So we'll save that. And now when we go to the cable, we'll set the geometry for the mooring line. So this is the initial geometry. It's not meant to be for calculating loads, just getting a starting position. That's reasonable. So we have on the cable here, we go to state. And first we edit the geometry. So first we go edit. But wait, before we do this, I'll show you a trick. Let's make a connection between the two models. So we have to tell ProteusDS that we want these two models to interact with each other. So we have master as the rigid body, the follower is the cable, and we want a point connection. And this decable follower node n, no, it's not constraining node n, so we just leave that at 0, and that means it's going to constrain the other end. This is the location where the constraint happens, and that's in terms of the rigid body frame. So we want it to sort of go below the keel. That's about 1.5 meters down. That's at the end of the cylinder there. So we'll save that. Now it won't update in here until we edit the state information for the line. So we go to state, we go to edit, and first we added the geometry. So we're at 30 meter water depth, maybe like a scope of 3 sort of thing. So 120 meters. We want to leave node n position at 0, 0, and height above seabed. We'll set that to 0. That puts the node n point there. You start to see things showing up in blue here about what's happening. So now instead of trying to set node 0 to close to where the buoy is, we just click, now that the connection is added, we just go match connection. And you'll see the mooring line go over here. Now one more thing, if we click on eject nodes from seabed, we see the line just running along the bottom, which is really nice to just prevent it from having to start off sitting in the seabed. The simulation will go a little bit slower. So it says, oh, hey, the line is pretty long, and you've got some line bunched up on itself. Maybe do you want to shorten the line? I actually want to keep it to be 120 meters. I'm okay with it pooling up on itself. So I don't want to adjust it, and go click no for now. Now you set the elements and the material properties for the elements. We've only added the 30 millimeter chain to this project so far from the parts library. So we'll do 30 meter chain. It's complaining, it's giving a warning indicating here that you have more geometry than you've allocated elements to it. The quickest way to resolve this is just hit resolve. And then you can see that it's automatically said, hey, you got to add enough material here for all your elements. Number of elements, we should have quite a few more than 60 meter elements. It's pretty long. Aim for 8 to 15 meters for shallow water chain kind of thing. But I mean, you can use your judgment and see what it looks like in the analysis. Then we'll go apply, and you can see we've got some information here set up for our buoy. And everything. So what I'm going to do is I'm just going to do a demonstration. Usually you run simulations for longer. You may want to run it with a sort of steady state current first to see what happens. But shallow water moorings usually, like, yeah, you'll have some deflection from currents, but the waves can really be a driver, especially in extreme conditions. So you can have some current profile on. Maybe just for simplicity, we'll put a uniform current profile on. 0.5. A heading of 0 is where the current is going to, and that aligns with the north direction here. We have the mooring lined up here. We're going to turn on waves. So we'll do 8, which is the John swap spectrum here. Right click, resolve follower properties, and maybe we'll pick something a little crazy. 10 meters, 13. And then what I want to do is have a little bit of a wave ramp duration. So we'll ramp it up over 10 seconds just so the buoy doesn't start off in a wave trough. Things will ramp up very quickly, but we'll see what happens. So let's save it and run it. So the idea here is you're running this analysis, seeing what happens to the buoy in currents and waves. I didn't turn on wind, but that's another thing you can do. And you would run the simulation, see what happens to the buoy, see what happens to the loads in the chain, and then decide whether you need more scope, whether you might need a bigger chain size, or maybe a mid-water float or something like that. You can adjust the design that way. So we'll let this run for a while and then check on it and run a report to see the results. All right, some time has passed. Now let's check the results of our simulation. So we'll click on this Post PDS button here in the toolbar, and that'll load up the results in the 3D Visualizer tool. Remember that we've got about 60 seconds worth of simulation time. That's pretty short, but the idea here is you would be looking at the results and kind of gauging if you need longer results, just kind of looking at the peaks and things like that. And we have training videos to help give you some guidance on that kind of thing. So we'll load all the data here. And you can see here's our little 3D kind of view of the ocean. The buoy's a little kind of default gray color. Maybe we might want to right click on that, DB8000, set it to be nice bright yellow color. So the buoy's got to settle a little bit. Remember we turned waves on to ramp up over 10 seconds, so it'll take a little bit of time for the waves to start showing. It's kind of a little bit easier to see what's going on with engineering view. We can double click on the buoy to sort of center the grid over there, and you see the waves ramping up quite a bit. So there's lots of things you can do here in engineering view. You can look at the nodes just to get a sense of, is the mesh good enough? You get some experience with sensitivity studies with that over time to build your judgment. Get nice views of sort of like what does the tension look like in terms of a color plot. Things are very transient right now, so I don't think we'll see too many things. There's lots of different kinds of plots you can see in here, though, like tension over time. The way that we set it up is element 1 is right under the buoy, so you can see some peaks forming there. And we'll see over time a bit of drift happening because we haven't really quite got it at the steady state mooring position. But for shallow water moorings, this is the point of jumping straight to dynamics. Like you kind of, you pretty much can get pretty close to that right away, especially in such shallow water depths. So yeah, we generated a lot of data. Now I want to show you the legacy report tool will help automate post-processing and pick out the peak tensions for you. So you can see like it's a little bit under 12. 12 kilonewtons is the peak tension. So we'll just close all this, go back to Simulation Toolbox, our legacy report here. We'll pick rigid body mooring. So this picks out, the rigid body. You're going to get some information on the floater motions and then the mooring. If you scroll down a little bit, there's report start time. I always like to chop off at least some time, when there's some transient kind of stuff happening at the beginning, like 10 seconds. If you want, you can report it in kilonewtons. This is a pretty basic report tool, but it gives you everything that you need. So it's done the post-processing, and you can click view. It makes a little HTML report. And you can see the maximum tensions here at 11 kilonewtons at the top, and then reaction loads at the where the anchor position is, and so on. They're pretty low, but again, it's not a lot of data in here. So I mean to say there's not a lot of data, that we only ran 60 seconds of simulation. We'd probably run it quite a bit longer and get a good sense of like what the peaks loads are and different things like that. So I wanted to give a sense of what the workflow looked like when you have a shallow water mooring and a pretty big buoy and you're a little bit concerned about the inertia values. This was a rough kind of guide to get going. It is going to matter, like the details of the buoy that you have. You need to make sure you have those, like the center of gravity position and stuff like that sorted out so you can put it in the software. But otherwise, it's pretty straightforward, as you can see, to make the connections to the mooring line. You can use more than one mooring line if you want as well. There's other video tutorials on that, but this is, with a single mooring line system. And yeah, that's what I wanted to share with you. So thanks for watching.